be able to take their inverse operator on both sides. And that will cancel them out. Which leaves us with the simple conclusion that the eigenvalue satisfying this exists. In fact, that eigenvalue is the very same eigenvalue we used at the start. There's no change. However, as you might have guessed, things are not so simple when looking for an additional solution to LZ instead. So, what happens when we do that? Well, let's say we already know LZ F naught is equal to lambda F naught. Now, I'm going to guess that LZ L plus F naught is equal to C L plus F naught for some C. Is this true? Well, we can still do the L plus commutation trick here, but it's not going to be as slick on this side. Why? Because L plus and LZ do not commute. In fact, the commutator of L plus and LZ is going to be what? Well, since this is a linear operator, it can be broken up into Lx LZ plus I Ly LZ. And, well, we explored what these are going to be last time, but in the short term, this is going to be, I believe, minus IH bar Ly, and this is going to be IH bar Lx. Then, that means I times I becomes minus, and forgive me, but I'm going to erase this part. What is this going to become? Well, once you factorize out all the garbage, at the end of the day, it should still just become minus h bar times Lx plus ILy. In fact, the commutator of L plus and LZ is just minus h L plus. Minus h bar L plus, that is. So, what can we do with this info? Well, recall that the commutator of L plus LZ is, in LZ, is just L plus LZ minus LZL plus. So how do we use that info here? Well, we are still going to try and commute. We are still going to try and swap the order, just like we did on this side. But we're going to pay a little bit more attention to what we do. So this side is obviously still L plus CF naught. But what is this side going to become? Well, it's going to be L plus LZ F naught. But recall, at first, this was LZ L plus F naught. So, in reality, this is more LZ L plus F naught plus L plus LZ F naught minus L plus LZ F naught. So we can reorganize this to state L plus LZ F naught minus the commutator, or rather plus the commutator of, minus the commutator of L plus and LZ is equal to L plus times C F naught. Now, you can use the associative property here, and you can plug in what we know and make this plus H bar L plus. Then you can use the commutative property for an operator and a constant, and bada boom, bada bing. The next time you apply the inverse to both sides, well, these two will cancel out, and we're left with LZ F naught plus H bar is equal to C F naught. Now recall that since LZ F naught used to be equal to lambda F naught, this was the assumption, that means that lambda F naught minus C F naught, hold up. I forgot this. So this tells us that since LZ F naught is equivalent to lambda F naught plus H bar F naught is equal to C F naught. Or in other words, C is equal to lambda plus H bar. And you can probably guess that it would have the opposite effect if I had applied L minus instead. Okay, so there we go. Here's the elegant conclusion. You've got a ladder. Now, on this ladder, you've got eigenfunctions and their corresponding eigenvalues making up an eigenstate, and so on, and so on, and so on, and so on, and so on. Now, we start at F naught and lambda. We go up the ladder by adding H bar and multiplying by L plus. We go down the ladder by subtracting H bar and multiplying by L minus. And you can keep going up and you can keep going down. It's as simple as that, folks. And so now, is there anything else we need to know? Well, yes. Just like the ladder operator we used to solve the time-independent Schrodinger equation, we have a bottom row. But what you might not expect is that we also have a top